Hello everybody, welcome to the next talk in the YugabyteDB Tech Talk series. My name is Sid Choudhury and I'm the VP of Product at Yugabyte. Today I'm going to talk to you about how to get started with YugabyteDB on Kubernetes. Let's dive right in. What is YugabyteDB? We are a transactional high-performance database for planet-scale cloud services. We're actually purpose-built for the modern cloud era. On the API layer, we support both NoSQL and SQL APIs. We're wire-compatible with Cassandra, Redis, and PostgreSQL. On the core database engine, we have a new storage, sharding, and replication architecture that is completely cloud-native, that builds for the cloud era. It can tolerate failures. It can run in containerized orchestration systems like Kubernetes. And we'll look a lot deeper into the architecture and how it actually runs on Kubernetes. A little bit under the hood of a 3-node cluster. The data nodes of YugabyteDB are called as YBT server. We have each of those nodes are running, are using our DocDB storage engine. It's a highly customized version of RocksDB that's optimized and built for ever-growing data, large data sets. On the replication front, to ensure high availability, data durability, we use Raft-based distributed consensus. We use both for data replication as well as leader election. The concept of leaders comes into the system because of sharding. The system auto shards any given table in any of our APIs into these leaders and followers across all the nodes that are out there. There is an additional independent distributed service called YB Master, which is actually responsible for managing the shard metadata and also coordinating cluster-wide operations like rebalancing when new nodes get added or existing node dies. So that's what actually a 3-node cluster looks like. Now, what does starting a YugabyteDB cluster look like? And this is the manual deployment. You take 3 nodes, and first you have to start the in a 3-node system. You can run replication factor 3. That means 3 copies of data will be available. 3 copies of the YB masters will also be there for redundancy purposes. So you start out by starting the YB masters. You give them addresses of each other so that they know where to look for each other. You mount a persistent storage into the system and so on. And then you start the 3 YBT servers. And the YBT servers actually need the location of the YB master so that they can register themselves with the master, and the master can start owning the start to node information. Now, if we see what's happening inside is there is a need for ordered operations with an ordinal index. We need 3 YB masters, we need 3 YBT servers, and each one of them has a specific identity, YB master 0, YB master 1, YB master 2, and so on. Secondly, we need stable network IDs because we want to be able to refer to those instances using the same host name IP address as the pods come and go. Which is what happens in a containerized environment like Kubernetes. And last but not the least, there is a need for a persistent volume mapping so that as a database, we can actually store data on the file system. So if we map this world to Kubernetes, then we realize that let's see which API, Kubernetes Controller API, can we pick. First is replica set. Replica set is about running exactly same and identical pods, and they cannot use any persistent storage. They use only ephemeral storage, so the pod gets, if you lose the pod, then any data that the pod was accessing will go away. Second aspect is deployment. It's just a higher level of replica set. It handles rolling updates and recreation. It's the most commonly used controller API for stateless applications. Daemon set is the third kind. It's maximum 1 per node. We usually do use that for node level functions like doing infrastructure monitoring, using your New Relic agent and so on. Last but not the least is the job controller API, which just simply ensures that you have n successful completions. That's the contract between the deployer and Kubernetes. It's good for bad jobs like crons. Now, none of them are ideal for the kind of stateful application that we saw in the context of YugabyteDB, where we need ordered operations, we need stable network identities, and persistent volumes. Now, Kubernetes has been working on this problem for quite some time. Originally, the controller that Kubernetes came out with was called pet sets. It was an alpha in July 2016, and it took 1.5 years worth of lot of work from various people to actually bring a stable stateful set controller, which is the new name, and it's actually purpose built for stateful applications. So if we see, it actually provides the same ordered operations concept that I was referring to: startup, scale up, scale down, rolling upgrades, termination. All these can happen in an ordered manner. Each of the pods that get created have unique identifiers, so that if we have to respawn the pod, then will not lose their identity, and the cluster will not be treated as a new member. It will be the same member because it has data attached to it. And coming to the data attached, it's the need for a stable persistent storage. It's actually linked to the ordinal index and name, and you can actually ensure that the same persistent disk gets attached even if the pod gets rescheduled in a different network, assuming the persistent storage mechanism is actually a network storage mechanism. There is also a need in the stateful set world. What Kubernetes mandates is the need for a mandatory headless service, which actually does not do any load balancing for the requests that are incoming. You can only use that headless service to actually talk to the individual pods that have been spawned up. And smart clients, which is what clients are in the context of stateful applications, they can connect to all pods or one pod or two pod, depending on whatever their need is. So having covered the basics of stateful sets, let's see how we run YugabyteDB on stateful sets. Let's start with YB Master. And go through what that will look like. So what happens is the YB Master gets modeled as a stateful set, and here we have a 4-node environment, but we're going to run a replication factor 3 cluster, which means there will be 3 copies of the YB Master stateful set pod, and we actually have we have to create a headless service so that administration clients can talk to the individual pods, as well as we create a standard load balancer YB Master UI service, so that admin users who want to understand the state of the database can connect to the admin UI and look at the various cluster configuration information. From a YAML standpoint, let's look at the stateful set first. We have specified replicas as 3. That means 3 pods will be created. How we specify master addresses is actually by using the Kubernetes approach of the namespace service cluster local as the way, because this is a local service between the YB between each of the pods themselves. And then there's the various UI and RPC ports that need to be exposed to the stateful set. And finally, there is the volume mapping at the bottom. The headless service becomes headless by having cluster IP as none, and all it is doing is taking the same UI and RPC port and making them available via the headless service. So that was master. Is actually very simple. The T server is also very similar, other than the fact that here we actually have as many T servers as the nodes in the system, and we can, when we scale up or scale down the cluster, scale out or scale in the cluster, we're essentially adding and removing pods to the YBT server stateful set service. here is how the various clients are talking to these various services. The application clients, like application code, will use the Cassandra, Redis, and PostgreSQL compatible endpoints, and the YBT server's headless service to actually talk to the data nodes of the YugabyteDB cluster. Coming to the YAML, again, very similar to what we saw on the YB master side. Again, the T server is running in the same cluster, and we follow the same approach of talking to the masters. We expose a bunch more ports because now this is actually the data node, and we have a very similar headless service. So no complexity at all. YB master and YBT server are just two different stateful sets with their own services. Let's look at a demo of how YugabyteDB runs on Kubernetes, and we'll see all the things that we looked at in action. We actually have a full blog on blog.yugabytedb.com where we have gone through the steps. So I'll just jump right in there. Let me end the slideshow and go over to this blog and start following the instructions. So first I have to ensure that I have Minikube and kubectl properly installed and configured on my laptop, and that's exactly what I have done. So now I'm ready to follow the instructions. I'll first create a directory, and then I will download the stateful set YAML. It's there. Now it's asking me to change the YBT server replica from 3 to 4 so that we can actually show replica. This is the YB master replica. The next one is actually the T server replica. So I'll change it to 4 because we'll show scale out and scale in. So let me close it. So that is done. Now, in order to create the cluster, all I have to do is apply this YAML that I have changed. So I do that, and that leads to all the various services and the stateful set that we had previously discussed now getting up and running. So let's see the status of the various pods. Yeah, I can see that 3 YB masters are already running, and 4 YBT servers, because we made YBT server replica count as 4. They are also running, and we can also see the various services. So let's see the various services that have been instantiated. So there is the YB Master UI load balancer service, because that's what we can use to actually look into the UI of YB Master. There are the 2 YB Masters and YBT servers headless services and the various ports that they expose. And we can actually see all of this on the Kubernetes dashboard. So if I open that up, then I can see the 7 pods, the 2 stateful sets, and the various services all up and running. Let me go back, and now let's take a look at the YB Master UI itself. In Minikube, what we have to do is this command, Minikube service name, and -- URL. And that essentially gives us the exact URL that we can use to look into this load balancer service that we had previously instantiated. Here we can see that there's replication factor 3, and there are 3 T servers, and we can see the various T servers out here, and we can see that we're running 108 version of YugabyteDB here. All good. Now we can actually do some operational tasks. So for example, scaling. We are a retailer. We have to increase demand. We are seeing demand increase all of a sudden, and we have to dynamically increase the database capacity. So all we have to do is kubectl scale stateful set YBT server with the data node service, and replica says 5. When I do 5, then now instead of 4 4 pods, YBT server will have 5 pods from 0 to 4. And we can see the new node here. You see that now there are 5 YBT servers. So that's great. Now we can actually, let's say the demand has passed. Now we don't need these additional capacity. We don't need the additional throughput that comes alongside them. We want to go back to the minimum needed, which is 3 YBT servers in a replication factor 3 cluster. So all we have to do is do scale down using -- replicas equals to 3. And if I do get pods, I can see that YBT server 4 and YBT server 3 are the 2 pods that are getting terminated, because this is where we see Kubernetes using the ordinal index concept for stateful sets to take out those pods that were added last. YBT server 4 was added last, and before that YBT server 3 was added last, and as a result we took them out first. So now and we can see the same here. If we go back, we'll see that 2 of the nodes are not pretty soon at 60 seconds we'll see them lose the heartbeat with the YB master, and as a result they will marked as dead. So with that, now we're ready to perform some more day 2 tasks, and one of the challenging day 2 tasks especially in databases, given the state attached to them, is performing rolling upgrades. And thanks to Kubernetes though, and the concept of stateful sets, this is now made a lot easier, and database that has been in a database like YugabyteDB that has been purpose built for this world, where we are able to do rolling upgrades very easily by upgrading each pod one by one. We can see this in action. So let's assume that instead of running 108 version, which is what this version of YugabyteDB is, we want to run 104 version. So what we'll do is we'll use this command. All that is saying is go into the stateful set of YB master and replace the image specification from YugabyteDB Yugabyte latest, which is 108, to this version, which is 104. So I'll copy this and I will run it here. Now what's going to happen if I do get pods, I'll see that first YB master 2 will be terminated, it'll be upgraded to the new image, then it'll be brought back to running, and then YB master 1 will be terminated and it'll be brought back to running, and so on. And we can see that there is YB master 2 has been alive for 9 seconds, YB master 1 has been alive for 4 seconds, and now if we do this, all of them have been restarted with the new version. Let me get the URL back. Okay, now we can see that we are now running 104 version build 24, which is exactly what we asked YugabyteDB we asked Kubernetes to change to. Now we have just upgraded the masters. What we need to do now is to do exactly the same on the T server, so that the actual data nodes themselves also start using the new container image. So all we have to do is do same, but instead of the YB master, we do YBT server. And now if we do get pods, we'll see the same happening from 2 to 1 to 0 on the YBT server pods, and them getting upgraded. So with that, let me go back to my slides. We just saw YugabyteDB on Kubernetes in action. Want to draw your attention that YugabyteDB is a fully open source Apache 2.0 project. Welcome to visit our GitHub page, watch, star us. You can actually try out all the various steps I showed you today, as well as more. You can explore more of our APIs using even sample applications by going to our quick start page. And we offer a wide variety of installation options, Mac, Linux, Docker, and Kubernetes. With that, I have reached the end of my talk. Thank you very much. Hope to see you at the next Tech Talk.